Okay. Well, let me introduce our next speaker. I'll let him split the screen. This is Alan Lin. He'll be talking just broadly about zeta functions, but also some specific zeta functions. Okay. Doing the best sort of mathematics around. That's number theory. All right. On out.
Like you said, I'll be showing you some zeta functions. And I would like to give a special thank you to Dr. Lamphere for allowing me to work with him on this number theory, very interesting number theory topic. So number theory is the study of the prime numbers and functions related to them. Prime numbers are numbers that are only divisible by one in itself. 2, 3, 5, and 7 are examples of those prime numbers. These prime numbers are important because they're the fundamental units of all numbers, because any positive integer can be expressed as a unique factorization of those prime numbers. For example, 20 is 2 times 2 times 5, 36 is 2 times 2 times 3 times 3, and any number can be expressed as a product of those primes up to the order in which they appear. This is known as the fundamental theorem of arithmetic. Since these prime numbers are so important, we want to know some properties about them. For example, how far apart they are. The first few prime numbers, 2, 3, 5, 7, 11, are all very close. But as you go on into the number system, they'll be farther apart because there'll be more factors of each number. Euclid proved that there are infinitely many of these building blocks. He showed it in this way. He supposed that there's a finite number of primes. Say the first prime is P1, the second prime is P2, on to Pn. Then he defined capital N to be the product of all those prime numbers plus 1. Now, since n is greater than 1, n has to be either prime or composite. If n is prime, then n is not a prime, if n is prime, then n is prime not found in this list. If n is composite, then by the fundamental theorem of arithmetic, n can be expressed as a unique product of primes. But none of these primes, P1, P2, P3, up to Pn, divide n evenly. So there must be a new prime pk not in the set. In that way, Euclid proved that there are infinitely many primes. Since there are infinitely many primes, we want to see how many primes are less than a number. So we define this function pi of x to count the number of primes less than x. For example, pi of 10 is 4 because there are only 4 primes less than x, 2, 3, 5, and 7. Likewise, pi of 27 and pi of 100 is 25. But let's say we want to count the number of primes less than 1,000,000. Counting all those primes will be very tedious. However, in the 1790s, this mathematician named Frederick Gauss notes that as x becomes larger, the function x over log of x becomes a better approximation of pi of x. This is known as the prime number theorem. In other words, as x gets bigger, pi of x and this function becomes, in a sense, equivalent. Therefore, the limit as x approaches infinity of the quotient is equal to 1. So using this approximation, we see that the number of primes less than 1,000,000 is about 72,382, while in reality, there are 78,498 primes less than 1,000,000. And this estimate gets bigger, this estimate gets much better as x gets much bigger. The gamma function is defined as the improper integral from 0 to infinity of x to the power of s minus 1 times e to the negative x dx. This function is really useful because it allows us to use calculus to study primes. Using analytical continuation, gamma of s is a meromorphic function. That is just basically a fancy way of saying that gamma is complex differentiable everywhere except for the poles where it's not complex differentiable. Gamma of S has the functional equation gamma of S plus 1 is equal to S gamma of S. Therefore, if you know, say, the value of gamma of 5, you can find gamma of 6 and gamma of 7 and so on recursively. So using this property, one special value of the gamma function is gamma of 1/2 is the square root of pi. The Riemann zeta function is the most important function in number theory because it relates all the primes in a certain way. It's defined as 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s all the way up to infinity. Or we can express it in this summation 1 over n to the s starting at 1 and going on to infinity. Euler showed that this sum can be expressed as an Euler product, the product over all the primes in this form. This is known as the Riemann zeta function, named after Riemann in the 1800s. Euler defined zeta of S for all real numbers. Later, Riemann extended the domain to all complex numbers. He did so in his memoir in 1859. So Riemann showed that zeta of S is a meromorphic function with pole at S is equal to 1. He extended the definition from the half plane to the entire complex plane. He found a simple functional equation that does this. He related the value at S to the value of 1 minus S, where Z of S is this following equation. Notice how Z of S has gamma of S over 2 in it. Therefore, we can use calculus to study the Riemann zeta function. And the Riemann zeta function is the Euler product of all the prime numbers. Therefore, we can use the Riemann zeta function to study prime numbers. This is why the Riemann zeta function is so important. The Basel problem was a famous problem in the 1700s regarding the value of zeta of 2. Zeta of 2 is the sum of the reciprocal of squares, 1 plus the 4th, plus the 9th, plus the 16th, plus the 25th, and so on. This was really famous because the mathematicians at the time couldn't solve it, but Leonhard Euler did, and this is how he did it. He factored the function sine of x over x using the Taylor series, like so. He said sine of x over x is equal to this Taylor series, but then this function can be factored into its roots. And he multiplied all this out, and he got this. Now he said that since they must be equal, which is often very useful, the coefficients of the x squared terms here must equal the coefficient of the x squared term here. Likewise, the coefficient of the x to the 4th term here must be equal to the coefficient of x to the 4th term here. And same thing for the x to the 6th. In that way, he found the value of zeta of 2, zeta of 4, and zeta of 6, and so on and so on. So Euler found these values. He found that zeta of 2, the Basel problem, the sum of the reciprocal of squares is pi squared over 6. When you first look at this, this is crazy because you add up infinitely many rational numbers and you get pi and it's squared. And this is an adventure for another time, but the reason why pi is here is that there is this amazing geometric interpretation of the Basel problem that you can search up for yourself. Zeta 4 is the reciprocal of all the natural numbers to the 4th powers, and that's pi to the 4th over 90. Zeta of 6 is pi to the 6 over 945. And zeta of 8 is pi to the 8 over 9,450. Also, here are some additional values. Zeta of -1 is -1/12. Zeta of -3 is 1 over 120. Zeta of -5 is -1 over 252. And zeta of -2 is 0. Euler found a general pattern for all these values. He noticed that for all positive even integers, this is the formula used to compute it, where b of 2n is the 2n Bernoulli number, and that can be found by this generating function. So if you want to find zeta of 2, you plug in 1 for n, and that would give you pi squared over 6. If you want zeta of 4, you plug in 2, and that would give you pi squared 4 over 90. And this formula gives you infinitely many values. Likewise, he found a general formula for the negative integers. Since all odd Bernoulli numbers is equal to 0, if you plug in negative 2n, you get b of 2n plus 1. But b of 2n plus 1 is 0, since n is odd. Therefore, the Riemann zeta function at negative even integers is 0. There are loads of generalizations of zeta of s. For example, the Hurwitz zeta function is defined as the summation from 0 to infinity of 1 over n plus q all to the power of s. Notice that the Hurwitz zeta function at s, 1 is equal to the Riemann zeta function. In other words, if you substitute 1 in here, you get the Riemann zeta function. The Hurwitz zeta function also has an analytical continuation, and the following is its function equation. Notice again that it has gamma of s in here, which means that we can use calculus to study this function. Another zeta function is the Lurch zeta function, and that is a generalization of the Hurwitz zeta function. L of lambda alpha s is a summation from 0 to infinity of e to the power of 2 pi I n lambda, all over n plus alpha to the s. If you think back to the Hurwitz zeta function, the numerator was just 1, but now we replace it with e to the power of 2 pi I n lambda. The Lurch transcendent is very similar. It is z to the n over n plus alpha to the s. Therefore, phi, the Lurch transcendent of e to the power of 2 pi I lambda alpha s is equal to L lambda alpha s. Dirichlet characters are also used to study primes. A Dirichlet character is a function chi that takes in any integer and outputs complex numbers if it satisfies the following conditions. There exists an integer k such that chi of n is equal to chi of n plus k. You can think of this like the sine function. It repeats itself for a certain period. Also, chi of n is 0 if the greatest common denominator is greater than 1, and chi of n is not equal to 0 if the greatest common denominator is equal to 1. And finally, chi of n is completely multiplicative. In other words, chi of n times n is chi of n times chi of n. The principal character is chi of 1, and is given by the following piecewise function. Chi of 1 of n is 0 if the greatest common denominator is greater than 1, and chi of 1 is 1 if the greatest common denominator is 1. If chi is a character mod k, then so is its complex conjugate chi bar. Using these properties, we can find some values using Dirichlet L-functions. These functions are a new class of functions that are used to study primes. Here is a table of the Dirichlet characters module 7. Okay. The Riemann zeta function is a special type of a Dirichlet L function. Recall that it is the summation from 1 to infinity of 1 over n to the power of s. And it can be expressed as an ordered product, like so. A Dirichlet L function is a function of the form L s chi is equal to the summation of chi of n all over n to the s from 1 to infinity. Its infinite product expansion can be expressed as this. Using the power of Dirichlet L functions, we can show that there are infinitely many primes ending in the digit 1, 3, 7, or 9. You could prove that there are infinitely many prime numbers, but with this new function, we proved something even better. We proved that, well, not we, Dirichlet proved that there are infinitely many primes ending in 1, 3, 7, and 9. We want to find the values of our own Dirichlet series. So Choi studied this double integral. we define d Choi plus or minus of SAB as the alternating series of 1 over an plus b to the power of s plus or minus 1 over an plus a minus b all to the power of s. And we define d plus minus SAB as the non-alternating series. Choi found values of d Choi minus of 2ab for 5 distinct values: 4, 1, 8, 1, 12, 1, 16, 1, and 21. He did this by solving this integral for distinct values of p. We can use his series to define a Dirichlet L function, namely like so. Under the constraints, the real part of s greater than 1, a and b are coprime, a is greater than 2b, and a and b are natural numbers. Choi obtained the following 5 values. D Choi minus of 241 is equal to pi squared over 8 radical 2. D Choi minus of 281 is 1 over 32 times the square root of 5 plus 7 over radical 2 times pi squared. D Choi minus of 212.1 is this value. D Choi minus of 216.1 is this value. And finally, D Choi minus of 221 is equal to this value. What Dr. Lanphier and I did is that we found infinitely many values. We found a general formula that if you substitute numbers in, it will give you a special value. First, we saw that d Choi plus or minus SAB is a meromorphic function because it can be expressed as a linear combination of 2 large Zeta functions. Therefore, if this has a meromorphic continuation and this has a meromorphic continuation, this must also have a meromorphic continuation. We also found that d Choi plus or minus of 1ab all squared is d plus 2ab. In other words, this series squared is equal to this series. If we take the derivative of d Choi plus or minus of SAB, we get negative s d Choi minus of s plus 1ab. Using this property, we can find a formula for d Choi minus of 2ab. Just take the derivative with respect to b of this, and we have the following formula. We can also get d Choi plus of 3ab by differentiating this formula again with respect to b. And if you keep differentiating with respect to b, you get a new formula. So here are all the formulas we found. We found d Choi minus of 2ab, d Choi plus of 3ab, d Choi minus of 4ab, and so on for d Choi minus n even and d Choi plus n odd. And we know using methods how to what the value of these d minus and d pluses. There are methods for computing the exact values. So therefore, if we know the exact values of these, we can find the exact value of d Choi plus and minus. And using those formulas, we found these values. D Choi minus of 283 is this value. D Choi minus of 251 is this value. And finally, D Choi plus of 341 is this value. Again, using these formulas, you can substitute any a and b in. They have to be natural numbers, but you can substitute any a and b, plug it in here, and get an exact value for that function. And that's it.
Okay, thank you very much. Let's thank our speaker. Thank you, good job. Okay, Racken. All right. So are there any questions that any of you have for Alan?
Sure. What sparked this research?
Well, Why do you do math, basically, is the question you're trying to ask. Well, some people do math because like it can be applied to real world problems, and primes can be applied to real world problems, like for example, coding, algorithms, and cryptography. But I like to do math because it's fun, and you do it just because. It's like comparing a hiker climbing Mount Everest. You might ask him or her, why do you climb Mount Everest? There's no purpose to it. It doesn't contribute anything. And he or she will reply, yeah, you're right. It doesn't contribute anything, but it's fun and I want to do it.
Well, let me say for this particular project, Alan said, I'm interested in the Basel problem. And we tried to kind of, my unwritten number theory book is a book starting called The Basel Problem, which collects, there are literally 100 proofs in the literature. And I say literally, I believe that there's like 100 proofs in the literature of this. The sum of 1 over n squared is pi squared over 6. So we were trying to say, okay, let's try and take one of these proofs and generalize it and play with it. And we were just doing that and going here and there, trying different things, nothing really going on, but just trying it. And then bang, we saw that we were able to generalize these results of this mathematician named Choi. He says, I'm not generalizing the Basel problem, but we're getting special values of these other Dirichlet series, which this other guy has studied. And so we got that. That was kind of nice. However, I mean, if you ask the general question, why do you care about special values of L-functions or special values of Dirichlet series? Dirichlet series, what you, in the world of mathematics, if you don't want to do this, Al, but the world of mathematics, you have a bunch of kingdoms. You have the combinatorics group, the logic group, but the two great kingdoms are the analysts and the algebraists, and the algebra is, let's say, arithmetic. You have an analysis and arithmetic, okay? And they're very different. What does an analyst do? An analyst says something is 0 because it's so tiny that it's smaller than anything. An algebraist says something is 0 because if you multiply it by something, you get the same thing, okay? It has a property of 0. And do these two kingdoms intersect? Yes, they do. What's in the intersection? Zeta functions, okay? So zeta functions allow you to use calculus to attack arithmetic. And any properties of zeta functions are interesting. So I'll let Alan continue.
Hopefully that answers your question.
Other questions?
Are you going to continue this research? And if so, what area do you think that will lead you into?
Yes. Right now, we're thinking of, instead of those choice series that we found, instead they have a numerator of 1. We've been thinking about generalizing that even more, like say have complex arguments over that, and we're trying to see what values we find there.
Okay. Any other questions? All right. Well, let's thank our speaker again. And the next talk will be at 4 o'clock. It'll be last talk in the session. Okay, thanks a lot, Alan. And did a great job. Okay. Are you ready?
Yes.
Okay. All right. The last talk of the session is Kate Thompson, in collaboration with Cameron Jackson and Dr. Shane Palmquist, and she'll be speaking on engineering numbers, innovation of quantification.
Hello, everyone, and good afternoon. My name is Kristen Tate Thompson, as he said, and I will be speaking on behalf of my good friend and fellow civil engineering student, Cameron Jackson, and one of our professors who we did research under, Dr. Shane Matthew Palmquist. And the title of our research is Engineering Numbers, Innovation of Quantification. So I wanted to start this discussion with the purpose of our research. The purpose of this research, we started it to start a discussion. It wasn't potential. We didn't go into it with the idea that we were going to solve an issue, but we were tasked to find a potential reason that our current mathematical system doesn't account for division by 0. This research, again, I want to emphasize, does not solve the issue. It is just a start in making an argument that division by 0 could potentially be, or is, more than just undefined. So we use numbers every day in every field, but what are they? So my definition is a number is a mathematical object created to allow people to better understand and know the world around them through knowledge involving measure and quantification. Now I had the word created underlined. What could it possibly mean the numbers are created? Mankind, humans, have created numbers to develop a better understanding of the world around us. They are continually developed over time to meet the demand of humankind to better understand the universe. So as mankind has become more advanced, so has mathematics. This is very important for science and mathematics to be able to grow with mankind, that our numbers also develop and expand. So here are the basic distinctions in the type of numbers we have. We have ordinals versus cardinals, ordinals being the order, first, second, third, cardinals being size or magnitude, measurable, which is our finites, and our immeasurables, which are our infinitesimals and infinities. We have our complex versus real numbers and our positive versus negative numbers. So this is a current depiction of the Venn diagram of the sets of numbers we use in practice. An integral part of our research was the uniqueness of a number. An important characteristic, and arguably the most important in each number, is that they are fundamentally unique. So while numbers can be similar in size, such as 2.01 and 2.010001, those numbers are not the same. They do not equal each other. They're very, very close to each other on the number line, but they are not equal. We found an issue with our current mathematical system that we can write the same number an infinite number of ways. And if I just explained how important uniqueness is to a number itself, how can we write one number an infinite amount of ways? Oh, here again, how is it that we can represent a single number an infinite number of ways? In our current mathematical system, infinite and decimal expansion allows for us to write numbers an infinite number of ways. For every finite number, there's an infinite number of zeros that trail to the right side of the decimal place. So we have some examples, which we know pi goes on infinitely with no repeatable pattern. To contrast that, we have 2/7, which has 6 numbers that repeat on and on forever to infinity. And to contrast both of those, we have 12/5, which we would write in practice as 2.4 to do calculations, but mathematically it equals 2.40 repeating to infinity. So 7 is not equal to just 7. Mathematically, it equals 7.0 to infinity. We never write these zeros out, but mathematically they exist, they're there. And this is true for all finite numbers. But in mathematics, it is important that we're concise and also have a quantitative number that we can write down. And this is where scientific notation comes in. Scientific notation is a method of presenting a very large or very small number in a concise, clear, and consistent form. So we have the general equation p times 10 to the nth power, where p is a number 1 through 10, which are all significant figures, and n is the number of places you move the decimal point, which if you move it to the left, it's going to be positive, and the right, it will be negative. So we see in this example, we have a very large number that can also be written in a small, consistent form that makes it easier to transcribe. Maybe you are less likely to miss a group of zeros or not write any extra down. So I mentioned significant figures. All the values written for p in the previous equation are significant figures. The current rules for significant figures are as follows. All non-zero numbers are significant. Zeros between non-zero digits are significant. Trailing zeros after the decimal are significant, and leading zeros are not significant. So what makes scientific notation allowed in our system is that it's both concise, but it has an answer which is measurable because significant figures are measurable. So from our research, we concluded that we already have a well-established and concise way of writing numbers and a system in which we produce an accurate measure. If significant figures work so well in calculations with scientific notation, why can't we generalize this to a set of applied numbers? So here's where we propose our idea of applied numbers. Because we argued that uniqueness is a fundamental property of all numbers, and that each number is unique in terms of size from all other numbers, to increase uniqueness, we propose using scientific notation to produce numbers with a finite decimal expansion. So what does this solve? Why does this matter? We believe it is not reasonable in mathematics that there are an infinite number of unique ways to write the same decimal number. This allows for the common misconception that 0.9 repeating equals 1, which equals 1.0, and so on. Mathematically, fundamentally, we know the difference between 0.9 repeating and 1. They are approximately the same, but they are not equal. If you were to put them on a number line beside one another and zoom in on it, there would be an infinite number of infinite decimals between it. So we know they're not the same. They do not equal each other. They are approximately equal. So here's our proposed new set of numbers. You can see the two pink sections that have been added to both the real and imaginary sides. These are our imaginary applied numbers and our real applied numbers. So here we are proposing the expansion of our current number system, adding a set to expand what we already have. So if a number has infinite decimal places, that's fine. It just doesn't work in the applied number system. As humans, we operate in the applied number set because we're not computers. We can't calculate an infinite amount of repeating zeros that go on to infinity. So here's the first example. We can see on the applied number side, we get the answer of 461.4792 when rounded properly according to the current rules we have in place for subtraction and addition of significant figures. We get 461.5. You can see that the unrounded answer is also on the mathematical number side, but it also has an infinite amount of different ways you can write that same answer, which again begs the question of uniqueness. How can the same problem have infinite amount of answers that are equally all correct? Here we have an example with subtraction, the same thing. When rounded, the applied numbers answer will be 511.4. And we have the unrounded answer on the mathematical side, but also infinite number of ways to write it. So what is the motivation for this? By making numbers more unique, we may better be equipped to understand and interpret our number system. This paper is just a stepping stone. Again, not an answer, not a solution, to find the potential for expanding our current number system. We believe it is unacceptable that the only solution to division by zero is undefined, and this may just be the start of uncovering a different answer. Our research began with looking for another reasonable solution to division by zero. Thank you for your time, and does anybody have any questions?
I have a question.
Yes.
Would this new system expand to quaternion and higher dimensional numbers?
I believe so. It would apply to everything we can mathematically do, like humanly do. So yes.
Okay.
Anyone else?
I'll just mention this kind of leads back into the previous presentation where if basically right now mathematics requires that there's an infinite number of decimal places. And what we're proposing is sure, I have no problem with that. Let's keep that as well, and let's expand, and let's not only allow for an infinite number of decimal places, but also a finite number of decimal places as well. And so then that kind of ties in with what I had said sort of in the previous with Brian's paper, where you have 0 being 1 divided by infinity, and then 0.0 being equal to 1 divided by 10 infinity. So again, it's just kind of begging the uniqueness thing. And the one thing that's interesting about all of this is and Cameron, can you switch back to that Venn diagram of all the numbers with the pink applied? So the interesting thing I think in all of this is no matter how we cut the cake, we're always working with these applied numbers because there's always only a finite numbers that we're able to write down, either by hand or by computer. So we're sort of always working with these applied numbers, whether we like it or not. I think it is important to have distinctions, and I do like having all these other sets as well, in terms of characterizing different types of numbers and understanding better the nature of numbers. So anyways, I'll be quiet.
Also, I'm looking at that, and I was just wondering on how it's set up. So is there a number that's not real and not imaginary, but still part of the complex numbers?
Jane, I'll let you take that one.
Sure. I mean, by definition, a complex number, if we go with the traditional approach, the A plus BI, approach, you must have a real part, and that real part could be 0. It could be a non-existent quantity, if you will, but then it would have to have an imaginary part. So I hope that answers your question. I mean, by definition, a complex number has some sort of real part, some sort of imaginary part.
I see. Yes, thank you.
Right, any other questions? Okay, let's thank our speaker again. And thank you all very much for attending. I hope you had a good time and learned a lot. So that's it for the sessions. That's it for this session. Tell all your friends how wonderful it was for you and publicize it. And thank you very much, everyone, for attending this session of the symposium.